Welcome to the deep dive. Today we are really getting into the plumbing of modern AI, specifically looking at knowledge graphs, or KGs.
That's right. These KGs are basically the structured brains behind a lot of the smart applications we use every day.
Exactly. Things like sophisticated search, question answering, even entity linking. If you're wondering how your search engine figures out which Michael Jordan you mean when you ask about him and LeBron, well, KGs are the key. They're foundational.
Absolutely. Think of the internet as this enormous, messy library with books constantly being added and rewritten. The knowledge graph tries to be the clean, organized card catalog for all that information. It connects entities, people, places, things with defined relationships.
But building and maintaining that catalog, especially when the library keeps changing every second, that sounds like the real challenge.
Oh, it's huge. And that's what we're diving into today. It's this constant battle against, well, what people often call the 4 Vs of big data, but applied specifically to knowledge.
Right, the volume, just the sheer amount of web data, variety, all the different ways information is presented, veracity, is it even correct? Lots of noise and conflict out there, and velocity, how incredibly fast everything changes.
Miss any one of those, and your KG starts becoming obsolete almost instantly. It's a tough problem.
So our mission today, for you, the learner, is to trace how one major system evolved to tackle this. We're going from the early days with a platform called Saga right up to the current state-of-the-art ODKE plus MIRI. It's really the story of automating knowledge ingestion at scale.
Precisely. Understanding this journey gives you a blueprint for how you build a backbone for truly semantic applications.
Okay, let's start at the beginning then. You mentioned Saga. This sounds like the necessary groundwork before you even think about extraction.
It is. Saga was and is the underlying platform. Think of it as the heavy-duty infrastructure designed for continuously building and serving this knowledge graph at a massive scale. It handles the storage, the serving, the basic management.
So Saga holds the data, but making that data smart, making it useful for AI, that requires something more, right?
Yes, that's where the machine learning extensions come in,
Yep.
built right on top of that graph structure. And one of the very first absolutely critical steps is creating graph embeddings.
Embeddings. Okay, we hear this term a lot. Why are they so crucial? Why can't the AI just, read the graph directly?
Well, most machine learning models, especially neural networks, they thrive on numbers, on dense vectors, not so much on these discrete symbolic structures like a raw graph.
Ah, okay.
So embeddings translate that complex web of entities and relationships into a mathematical space, a vector space. They turn relationships into distances, essentially.
So things that are conceptually similar in the real world, like maybe two different types of scientists, end up closer together in this vector space?
Exactly. That proximity, that neighborhood in the vector space, is what the models use to reason and make inferences. It's the key enabler for several core capabilities.
All right, let's break those down. What can you do once you have these embeddings?
Okay, 4 key things initially. First, fact ranking. So imagine an entity like LeBron James. The KG might list multiple occupations. Basketball player, maybe TV actor, screenwriter.
Right, he does a lot.
He does. The embedding model helps figure out which fact is most central or important. So for a general query, it ranks basketball player highest.
Makes sense. What's
Fact verification. This is huge for dealing with let's call it messy data from the web. The embeddings help the system assess if a new fact seems plausible or if it conflicts with existing high-confidence knowledge.
sort of an initial sanity check?
Pretty much. Third is related entities. Because similar things are close in the vector space, the system can proactively suggest related items. You search for one movie director, it suggests others you might like. Enhances user experience.
And the fourth one sounds critical for search. Entity linking.
Absolutely critical. Entity linking is the process of figuring out which specific KG entity is being mentioned in a piece of text, like a user's search query or a news article.
So disambiguating Michael Jordan, the basketball legend from Michael Jordan, I think there's a machine learning professor with the same name.
Exactly that. The embeddings, combined with context, allow the system to link that text string to the correct unique ID in the graph. This is fundamental for understanding user intent.
And this linking challenge naturally leads to the next big hurdle you mentioned, semantic annotation. Trying to connect the entire web back to the KG.
Yes, linking the web. The goal is to add edges from the KG entities to all the unstructured documents out there where they appear.
That sounds astronomically difficult. The scale.
It's immense, hundreds of billions of pages. Think of a news alert. Root hits 100 as England turned the screw. The system needs to instantly link the strings Joe Root and England in that headline back to their unique entities in the KG.
And the challenges are not just volume, right? It's languages, pages changing constantly.
All of the above. Multilingual content, high rate of change, and you have to do it cost effectively. You simply cannot crawl and re-annotate the entire web constantly. It's computationally and financially just, well, impossible.
So that constraint, the impossibility of boiling the ocean, that must have forced a more focused approach. Is that where ODKE version 1 comes in?
Precisely. Open Domain Knowledge Extraction, ODKE v1, was born from that reality. It was a shift towards targeted information extraction.
Targeted. How so?
Instead of trying to extract everything, it focused on fixing specific known problems in the KG missing facts, or facts suspected of being stale. It became reactive.
So it would find a gap, like this person is missing a date of birth, and then go looking.
Exactly. It would analyze query logs, what are users asking for that the KG doesn't know, or it would proactively profile the KG to find important entities missing key attributes. Then, crucially, it would auto-generate very specific search queries just to find evidence for that missing piece of information.
Ah, so instead of a wide crawl, it's doing surgical strikes with search queries. That tackles the volume problem in a practical way.
It was a pragmatic start. Only fetch documents likely to contain the answer you're looking for.
And the source material had a great example of this in action, finding the birth date for Michelle Williams.
Yes, that's a perfect illustration.
Yeah.
The system flags Michelle Williams, a significant entity, as missing a date of birth. It generates search queries,
Okay.
and the search results bring back evidence for two different dates, July 23rd, 1979, and September 9th, 1980.
Because there are two famous Michelle Williams, right? The singer from Destiny's Child and the actress.
Exactly. So ODKE v1 couldn't just grab the first date it found. It had to use corroborating signals in the source documents, mentions of Destiny's Child versus mentions of film rolls, linked images, that kind of thing, to correctly deduce that the 1979 date belonged to the music artist.
So targeted search, pattern extraction from the results, and then this crucial corroboration step to resolve ambiguity. That was the core of ODKE v1.
That was the initial architecture, yes. It proved the concept was viable.
But I guess the sheer speed and messiness of the web meant just reacting to gaps wasn't enough long term. The velocity and veracity issues would still overwhelm a purely reactive system.
Absolutely. Search-based extraction is good, but it's inherently limited by search index freshness and what patterns you can predefine. To really keep up, the system needed to evolve. This brings us to ODKE v2.
Okay, so what were the big leaps from V1 to V2?
V2 is about scaling up and becoming more proactive. A major addition was crawl-based evidence retrieval. Instead of only relying on search, it started proactively monitoring known, high-value, high-trust sources.
Like Wikipedia.
Wikipedia was a prime example. If you know a source like the English Wikipedia index is generally reliable and updated frequently for certain types of facts, you prioritize crawling and monitoring it directly, rather than waiting for a gap to appear or relying on a general web search.
That makes sense. Were there other big changes in V2?
Yes, several. This is where they started experimenting, albeit in a limited way initially, with LLM-based extractors. They also added multilingual support, which is crucial for a global KG. And, importantly, there were major improvements to stability and throughput.
Throughput, just processing more facts faster.
Dramatically faster.
Yeah.
ODKE v1 could handle maybe around 5,000 facts per minute. V2 pushed that up to potentially 100,000 facts per minute.
Wow, okay. That's a huge jump in scale.
It had to be, because the maintenance challenge itself is just staggering. The source mentioned a figure that really highlights the velocity problem. Around 2 million English Wikipedia pages get edited every month.
2 million. Just on English Wikipedia alone.
Exactly. The rate of change is relentless.
Yeah.
And this velocity leads directly to what they identified as the freshness gap.
The freshness gap.
Yeah, they did this deep analysis comparing when a fact appeared on a high-value source like Wikipedia versus when it actually made it into a structured knowledge graph like Wikidata.
And what did they find?
On average, facts appeared on Wikipedia a full 69 days earlier than they showed up in Wikidata.
69 days. So for more than 2 months, downstream applications, search results, smart assistants could be working with outdated information.
That's the problem. If you're asking about a newly elected official or the stats of an athlete in the middle of a season or, current market data, a 69-day lag makes the KG significantly less useful, potentially even misleading. User trust erodes.
I can see that. Are there specific types of facts that go stale particularly quickly?
Definitely. They identified common stale properties, things like a person's height or age change. Well, age always changes. Net worth fluctuates. Key dates like political appointments, relationships, current teams for athletes.
Hmm.
These need constant, rapid updates.
And freshness isn't the only problem. You also mentioned veracity dealing with conflicting information.
Right. The real world is noisy. You might get different values from different sources. The example given was the height of the NBA player Giannis Antetokounmpo.
What was the issue there?
One source might list his height as 2.13 meters. Another might say 211 centimeters. Now, mathematically, they're very close, but the variety of formats itself can cause issues. More importantly, sometimes sources just flat out disagree, or one source is simply wrong. The KG needs a robust way to weigh evidence and decide on the most likely correct value.
So V2 had to get better at handling both the speed of change and the conflicts in the data.
Yes, and alongside the extraction improvements, ODKE v2 introduced a really clever internal mechanism called the link inference mechanism. This wasn't about pulling data from the web. It was about improving the KG's internal consistency.
How does that work? Inferring links.
It leverages the inherent logic within the graph structure. For completeness, it can infer relationships. If the graph knows A is the spouse of B, it can automatically infer and add the fact that B is the spouse of A that's a symmetrical relation.
Okay, simple enough.
Or asymmetrical ones. If it knows A is the child of B, it can infer that B is the parent of A. These are usually very high confidence facts you can add directly, filling gaps internally.
Right. And how does it help with correctness, with veracity?
This is quite neat. It uses these high confidence inferred facts as a way to check the existing facts in the KG. Imagine the graph has an error. Maybe it says city A is located in county C.
Okay.
But based on lots of other reliable facts, maybe addresses of businesses in City A, locations of neighboring towns in Aspilis, the link inference mechanism strongly infers that City A is actually located in County B.
Ah, so the inferred fact flags a potential conflict with an existing fact.
Exactly. It acts like an internal auditor. It raises a flag, triggering a process to investigate that located in County C fact and potentially correct it. It's like the KG's own immune system finding inconsistencies.
So ODKE v2 scaled up, got faster, started monitoring key sources proactively, and built these internal checks. But you mentioned it only had limited use of LLMs. It sounds like it still wasn't fully equipped to handle the sheer complexity and unstructured nature of the broader web.
That's the perfect segue into ODKE plus EDIS. Version 3 is where they fully embrace large language models, but critically, they do it in a way that tackles the inherent risks of LLMs head-on.
Right, the big risks being
What?
hallucination, basically making things up, and maybe not structuring the information correctly for the KG.
Precisely those two. Hallucination generating plausible but factually incorrect information is poisonous for a KG that needs to be trustworthy. And lack of schema alignment, the LLM spitting out facts but not in the precise format, using the exact predicate names or units the KG requires, makes the output unusable at scale.
So ODKE Plus aims to get the flexibility and broad understanding of an LLM, but without the factual errors and the messy output.
That's the core idea. It was designed to overcome limitations seen in earlier attempts to use LLMs for this. Many prior approaches were often just batch processing experiments, not built for the continuous high-velocity nature of the web.
Okay, not production ready for live updates.
Right. They often lack strong corroboration mechanisms, making them vulnerable to hallucinations. And crucially, most were missing what ODKE Plus implemented: ontology-guided prompting.
Ontology-guided prompting, let's break that down. Ontology is the KG's schema, its structure, right?
Yes, the formal definition of entity types, properties, relationships, rules. If you just ask a generic LLM, tell me about this person, it might give you good information, but it won't automatically use your KG's specific property name for date of birth, or format the date correctly, or include necessary qualifiers like start date for a job.
And that misalignment makes automated ingestion impossible. You'd need humans cleaning up everything.
Exactly. It doesn't scale.
Yeah.
So ODKE Plus uses a modular pipeline where structure and verification are enforced rigorously at each step.
Okay, walk us through that pipeline. Where does it start?
It kicks off with the extraction initiator. Think of this as the system's trigger. It's constantly monitoring for signals, either known gaps in the KG, missing stale facts, or, very importantly, recent edits on high-value source pages, like those millions of monthly Wikipedia edits we talked about.
So it spots a change or a need. What does it output?
It generates a very specific instruction, a little package containing the subject entity, the URL of the document to check, and the language, the locale. Basically. Look at this page about this entity in this language.
Got it. That instruction goes where?
To the evidence retriever. This module fetches the actual document content, usually from that monitored Wikipedia index if it's a Wikipedia URL, or potentially using targeted search if it's another web source.
Okay, now we have the source text. Time for extraction.
Right, and this happens in the hybrid knowledge extractor. It's called hybrid because it smartly uses two approaches.
Which are
It uses high-precision, traditional pattern-based rules. These are great for extracting data from predictable, semi-structured sources, like Wikipedia info boxes or tables. They are fast and very reliable when the format is known.
But patterns can't handle just plain text paragraphs, right?
Exactly. So for broader coverage of unstructured text, it also uses flexible LLM-based extractors. You need both. Patterns for speed and certainty on known structures, LLMs for the flexibility to understand natural language text.
Okay, here's the crucial part then. How does ODKE Plus make sure the LLM extractor doesn't just hallucinate or output messy, unstructured data? You mentioned ontology-guided prompting.
This is really the heart of it. Dynamic ontology-guided prompting. Instead of giving the LLM a generic prompt, the system dynamically constructs a highly specific set of instructions, an ontology snippet, just for that extraction task.
A custom prompt for every single extraction.
Pretty much. This snippet is like a mini manual for the LLM. It tells it, for this type of entity, I need these specific properties, predicates. Here are their exact names. Here's a description of what they mean. For this property, you absolutely must provide these qualifiers, like a source date. And the value for that property must be in these specific units. For example, meters, not feet.
Wow, so it's guiding the LLM very strictly towards outputting structured, schema-compliant data. It's constraining its creativity in a good way.
Precisely. It forces the LLM to think in terms of the target KG's schema. And generating these snippets is actually a whole sophisticated pipeline in itself.
Ooh, what does that involve?
It involves first figuring out the most important properties for that entity type that's ranked property generation. Then enriching those property descriptions with all the necessary details like constraints and qualifiers, the predicate 360 view. And finally, generating normalization configs that specify the exact output format needed for values, like standardizing dates or units. All this gets baked into the prompt snippet.
That sounds incredibly thorough for ensuring schema alignment. But it still doesn't guarantee the LLM isn't just making up a fact that looks perfectly structured, right? The hallucination risk.
Correct. And that's addressed by the next absolutely critical module,
Hmm.
the lightweight grounder. This is the hallucination filter.
Okay, how does the grounder work?
It uses a second, separate, smaller LLM. Its only job is to act as a verifier.
A second LLM. Why not just ask the first bigger LLM to check its own work?
Good question. Self-correction in LLMs is often unreliable. The main extractor LLM is big and optimized for complex understanding and generation. The grounder LLM is small, fast, and highly specialized for one simple task.
Which is?
It takes the structured fact, the tribble, that the first LLM extracted, and it looks back at the original source text provided. Then it makes a simple judgment. Is this specific fact explicitly supported by the text? Is it directly stated or clearly implied in the evidence?
And the output is just yes or no.
Exactly. A binary decision.
Hmm.
Is it grounded in the evidence? Yes or no? Only the facts that get a yes are allowed to pass through.
That sounds like a really strong filter. Did it make a big difference?
A huge difference. The sources state this grounding step reduced the hallucination rate from the raw LLM output by about 35%. It's a non-negotiable step for building trust in the extracted facts.
Okay, so we've got facts that are schema-aligned and grounded in evidence. What's the final step?
The final module is the corroborator. This is where everything comes together for final polishing and decision-making. It does three main things: normalization, consolidation, and scoring.
Normalization first. What's that involve?
It's about standardizing the values based on those configs generated earlier. So if one source says NOF20 1980, another says 2011 1980, the normalizer, potentially using tools like duckling, which is good for dates, quantities, etc., converts both to the standard ISO format like 1980 1120. Same for units converting feet to meters, etc. Handles a variety.
Okay, standard formats. Then consolidation and scoring.
Consolidation groups together identical or equivalent facts extracted from potentially multiple sources or multiple places in one document. If the same birth date was extracted 5 times, it gains strength. Then scoring evaluates these candidate facts.
How does it score them? What factors does it look at?
Well, it uses a combination of heuristics and machine learning models. The score considers things like, was this extracted by a high-precision pattern or the LLM? What was the LLM's confidence score? How many different sources mention this fact frequent? How rich is the fact, did it come with all the required qualifiers?
So it's weighing all the evidence. And what was the impact of this final corroboration stage on quality?
This is where the precision really jumps. The raw, grounded LLM output might have been around, say, 91% precise, which is good, but maybe not quite good enough for a production KG where errors can cascade. After the corroborator does its work, the final factual precision reached 98.8%.
98.8%, that's incredibly high. That sounds like the level you need for industrial deployment.
It is. That leap from 91% to over 98% is what makes it trustworthy enough to feed directly into the main knowledge graph that powers downstream applications.
Which brings us nicely to those applications. This whole elaborate ODKE plus pipeline exists to create better KGs. But why does that matter? How does this high-quality, fresh, structured knowledge translate into better user experiences, especially in areas like semantic SEO?
It matters fundamentally. Semantic SEO is all about search engines understanding the meaning behind queries, understanding entities and their relationships, not just matching keywords.
Right.
So when you ask a complex question, the answer often comes directly from the KG. Think of those info boxes or direct answers at the top of search results. If the KG data powering that is stale, that 69-day lag problem, or inaccurate, even that small error rate before corroboration, the user gets a bad answer.
So better KG means better search snippets, better direct answers.
Exactly. ODKE plus delivering fresh, high-precision facts leads directly to more accurate question answering, better entity ranking, understanding which entities are most relevant to a query, and just generally cleaner, more context-aware web search results. It fuels the core components of semantic understanding.
Let's talk about the real-world deployment then. The sources say ODKE Plus went into production around May 2025. How's it performing at scale? Is it keeping up?
The production metrics are pretty impressive. In terms of scale, it had extracted something like 19 million facts covering nearly 200 different types of predicates or relationships. So broad coverage.
And throughput, can it handle the velocity?
Yes, it operates in two modes. There's a batch mode, typically run weekly, which can process a huge volume up to 6 million facts per hour. This is for deep, comprehensive updates.
Okay, for the big refreshes. But what about those high-velocity changes, like election results or breaking news?
That's where the streaming mode comes in. This runs continuously, processing 150,000 to 250,000 new facts every day, specifically targeting those high-priority, rapidly changing entities. And crucially, the end-to-end latency in streaming mode is under 2 hours.
Under 2 hours. Wait, so from a major edit happening on, say, Wikipedia, to that fact being extracted, verified, structured, and ingested into the live KG in less than 2 hours.
That's the pipeline speed. It's near real-time knowledge integration for prioritized updates.
That effectively crushes that 69-day freshness gap we talked about earlier.
It absolutely does.
Yeah.
They reported that ODKE Plus reduced the average update lag by 50 days compared to their previous workflows. That's a monumental improvement in freshness, which translates directly to more current and trustworthy search results and application data.
And they're maintaining that 98.8% precision in production.
Yes, sustained quality, verified through ongoing audits. That combination of speed, scale, and accuracy is the key achievement.
Okay, metrics are one thing, but the ultimate test, especially for something impacting search results, is how humans perceive the quality right. Did they check if users actually find the ODKE plus facts better?
They did, and this, for me, is one of the most compelling results. They conducted an extrinsic evaluation using human annotators.
How did that work?
They specifically sampled cases where there was a disagreement between a fact extracted by ODKE Plus and a fact already present in a well-established knowledge base like Wikidata. They showed these conflicting facts side by side to human raters without telling them which fact came from which system.
So a blind comparison, and they just asked the raters which one is better.
Essentially, yes. Which fact you prefer, which one seems more accurate, complete, or useful.
And the results.
In more than 90% of these disagreement cases, the human annotators preferred the fact generated by ODKE Plus fact.
Over 90% preference for ODKE plus facts when compared head-to-head against Wikidata in conflict scenarios. That's huge.
It's a massive validation. It shows that this complex pipeline, the ontology guidance, the LLMs, the grounding, the corroboration, isn't just producing technically precise data. It's producing data that real users find superior. And if humans prefer your facts, your semantic search applications are going to perform better.
It really demonstrates the value. Did the sources mention any specific semantic projects where ODKE Plus made a difference?
Yes, they highlighted work on trendy entity discovery. This focused on domains where things change incredibly fast, like identifying emerging actors, artists, influencers,
Mhm.
people who might not have established Wikipedia pages yet but are generating buzz online.
A really tough challenge for freshness and coverage.
Exactly. They used ODKE Plus to build new ingestion pipelines targeting popular online data platforms relevant to these domains. The system proved very effective at identifying and extracting information about these rapidly emerging, high-velocity entities.
Did it find entities that other systems were missing?
It did. In one case study, they mentioned 32% of the entities correctly extracted and disambiguated by the ODKE Plus pipeline were entirely new. They hadn't been captured by previous methods, and it did this while still maintaining over 95% precision.
So it's not just keeping existing entities fresh, it's also better at discovering the new important things, which is critical for staying relevant.
Absolutely. Better coverage, vastly improved freshness, higher accuracy, and demonstrable human preference. It all feeds back into creating a KG that allows search engines and other applications to move beyond keywords and truly understand the world of entities and their current state.
It really ties everything together, the embeddings for linking, the hybrid extraction for coverage, the grounding for truthfulness, the corroboration for precision.
The whole system is designed to produce that reliable, structured fuel needed to power the semantic web.
Okay, so looking back at this whole journey from ODKE V1's targeted search through V2's scaling and internal checks to ODKE Plus' full embrace of LLMs with rigorous controls, it really feels like a significant leap in automated knowledge-based construction.
It really is. It demonstrates a path forward. You can harness the incredible power and flexibility of LLMs for understanding the world's information, but only if you impose strict discipline. The keys are that dynamic ontology-guided prompting to enforce structure and that mandatory grounding step with a second verifier to ensure factual accuracy.
Those seem like the crucial innovations that make it work reliably at scale.
They prevent the system from just inheriting the LLM's weaknesses wholesale. It's about combining the strengths of LLMs with the rigor of traditional knowledge engineering and verification.
So, wrapping this up, what's the big takeaway for you, the learner, as you encounter more and more AI systems relying on knowledge like this?
I think the core lesson from ODKE Plus is that achieving trustworthy, high-precision knowledge generation from LLMs is possible, but it requires explicit verifiable mechanisms. Specifically, explicit grounding, proving the output connects directly back to source evidence, and strict schema validation, ensuring the output conforms to the required structure.
Which leads to a really interesting final thought.
Yeah, if this ODKE Plus blueprint works so well for building a reliable KG, how might this principle, using perhaps a second lightweight AI verifier to enforce truthfulness and grounding against source context, become not just best practice, but maybe even a required standard for any LLM application where factual accuracy is critical? Think finance, news reporting, medical information.
Could insisting on verifiable grounding be the key to building truly dependable AI across the board?
It might just be. It's certainly something worth considering as these powerful models become more integrated into our lives.
That is a powerful and essential thought to end on. Thank you so much for walking us through this incredibly detailed evolution of knowledge extraction.
It was my pleasure. It's fascinating stuff.
And thank you, the learner, for joining us on this deep dive. We'll see you next time.